Welcome to a new episode of ROHDE SCHWARZ's webcast. I'm Holger Rosier, Technology Manager for Connected Cars with ROHDE SCHWARZ in Munich. Today I would like to talk about Cellular Vehicle to Everything Communications, C-V2X. That's the mobile communications technology to connect road users. For more than 2 decades, engineers and scientists around the globe seek for solutions to connect vehicles to vehicles, vehicles to road infrastructure, to pedestrians, and in general, to everything. This technology promises to further increase road traffic safety, to make driving more efficient and more convenient. A couple of years ago, the analysts told us that the first autonomous cars will hit the streets in 2020. Pessimistic voices said, oh, this will not happen before 2030. Now we have the year 2020, and now we can read in reports that we will see probably autonomous cars in 2025. Pessimistic voices still remain with their forecast of 2030. But why is it so difficult to further increase the automated function we have already in the market? To try to explain it, let's first to the 6 levels of driving automation. These levels are defined by the Society of Automotive Engineers in the US, starting with level O, where cars do not have any supporting functions, to level 5, where with the full automation we have robot taxis on our street where it's not even necessary to have a passenger in the car. Most of the advanced driver assistance systems we have today in the market are mainly related to the partial automation, to level 2. Recently, automakers and tier 1s, they announced to roll out or to introduce level 2.+ functionality to the market, to show that they come closer to the level 3, but they haven't reached level 3 yet. What is so challenging to go from level 2 to level 3? Level 3 is the conditional automation. It means you as the driver, you are in general allowed to turn your attention to other things while driving the car. You can do home office, you can watch a video, you can read a book, you can do whatever you want. Your car is responsible to drive the car, and the car is able to perform almost all tasks and maneuvers in almost all scenarios. The emphasis lays here on almost all scenarios. It means that you must be aware of the traffic situation and ready to intervene. But now let us assume you have a laptop on your knees or a cup of coffee in your hand. How long does it take to bring you back into the control loop? The industry discusses that it takes at least 10 seconds. Now let us assume you are heading on a highway with 130 km/h. You have a state-of-the-art advanced driver assistance system with a forward-looking camera. This forward-looking camera has usually, in the best condition, a range of 250 meters. 230 km/h means roughly 36 meters per second. So this 250 meters is traveled in approximately 7 seconds. So this is not sufficient to inform you at least 10 seconds in advance when approaching a zone of hazardous road situation, for instance. And in my view, that's the reason why engineers seek now for wireless and mobile to increase the range of the sensors and of course also the visual horizon to that of the communication range. Wireless communication will help to smartly control the vehicle when we talk about level 3, 4 and 5. In these levels we are mainly talking about machine-to-machine communications. But wireless and mobile communications can of course also bring benefit to levels lower than level 3. But then we are mainly talking about warnings which are given to the driver. The applications which are enabled by V2X are assumed to be rolled out to the market in phases, starting with day 1 applications followed by day 1.5 and day 2 applications. In a short-term deployment, or what the industry wants to deploy in a short term, is, for instance, a use case like emergency electronic brake light. Cars inform if they do a harsh brake. Left turn assist is another example. When you want to turn to the left and there's a car coming in the perpendicular direction, then you get a warning on your dashboard. Intersection movement assist is a use case which assists you when you want to pass an intersection. Queue warning, a use case which informs you about a traffic jam ahead, so to give you the ample time to react and to slow down. In a midterm perspective, when the mobile or wireless communication system is able to offer a higher throughput, lower latency, and a bit more reliable, the industry wants to deploy use cases like see-through. A use case where you could subscribe to a video stream, which is advertised or sent by a car in front of you, so that you can learn more about the traffic situation ahead. It could give you the information if overtaking is possible or not. Real-time awareness, vulnerable road user discovery, speed harmonization are other examples. Sensor data sharing is then an important step towards cooperative driving, because with sensor data sharing, cars exchange sensor data, which means that they establish a kind of a distributed sensor network. And this kind of data can later be used to turn an autonomous car into a cooperative car. So in a long-term perspective, the industry develops solutions that cars can negotiate maneuvers. Just to give you an example, a car wants to merge into a lane and now negotiate the maneuver that other cars make a gap so that the car can merge. Remote control parking, data sharing for autonomous driving means that also sophisticated sensors can now offer data or transmit data, which means that the mobile and wireless communication system must be able to carry a high amount of data. Data offloading is a visionary use case where data and computational tasks are offloaded to the backend systems. Let us assume you have a car where the computational power is not sufficient to calculate a solution in a certain scenario. In this case, this computational task can be offloaded to the backend system. Mobile edge computing is here, for instance, a buzzword. The calculation is then done in the backend system and the result is provided back. We have today two competing systems in the market. On the one side, it's IEEE 802.11p, a technology based on wireless local area network. It's derived from IEEE 802.11a. The standardization started early this century. The finalization of the standard was ratified in 2010. It's a wireless local area network technology where you can establish a peer-to-peer ad hoc communications network. The frequency, which is intended to be exploited, is 5.9 gigahertz. This 5.9 gigahertz is a so-called ITS. ITS stands for Intelligent Transportation System frequency band. It's a band which is in almost all countries around the globe harmonized and which is offered or which is allowed to use in a license-exempt manner. Since 2016, 3GPP, this is a standard-defining organization responsible to standardize our smartphones, published in release 14 the so-called LTE-V2X feature. With LTE-V2X, vehicle-to-vehicle communications becomes possible. Since 2017, the standard is completely rectified. The industry term is cellular V2X, C-V2X. With this technology, it's also possible to establish a peer-to-peer ad hoc communication. And the targeted frequency range, the frequency band, is clearly, again, the 5.9 gigahertz frequency band. With this technology, cars are able to communicate to other cars via the so-called PC5 sidelink or direct communication. A car can also communicate to a pedestrian or to a road traffic infrastructure like a traffic light, to learn more about the signal phase and timing. Here it's important to mention that this kind of PC5 sidelink communication can be operated without any mobile infrastructure. You do not even need a SIM card to operate this kind of communication. In the next years, it's expected that all cars are equipped with mobile communications to provide access to internet-based services via the UU link. The UU link, this is the same link we use on our smartphones to have access to internet-based services, but now here in this case, it's deeply integrated into the car for vehicle-to-network communications. Vehicle-to-network communications give access to cloud computing, to edge computing, and as I said, in general, to all kinds of internet-based services. But for this UU link, you need the SIM card, you need the valid subscription to a mobile network operator, because the vehicle-to-network communication exploits the operator spectrum. What is now, from a technology perspective, the situation in the world? We have on the radio access layers the 3GPP radio access, a common single global standard. On top of it comes then, specific for each world region, for China, the European Union, for the US, different application protocol layers. In the middle, where they differ slightly in terms of bits, bytes, there are some different messages, but they share the common goal to increase road traffic safety, to increase efficiency, and to make travel more convenient. Also, the use cases or the application, they differ slightly. China, for instance, they favor 17 day one use cases. The deployment is expected this year, beginning of the next year. You will find almost similar use cases in the European Union and in the US. In the US, the system is called dedicated short-range communication or wireless access in vehicular environments. In the European Union, it's ITSG5, which stands for Intelligent Transportation System at 5.9 GHz. In China, it's called Internet of Vehicles or Intelligent Connected Vehicles. A couple of years ago, the 3GPP standard defining organization decided in 2012 to open a second branch for direct PC5 side-link communications. This feature was originally designed for commercial purpose, for short-range direct communications called device-to-device communication. Later, it was turned into a system which was advertised for police officers or fire brigades so that they can use their smartphones like they use their walkie-talkies. Later on, in 2017, the same feature was further enhanced to support and meet the specific automotive requirements, for instance, to cope with a higher relative speed of 500 km/h. Since then, the standard supports direct vehicle-to-pedestrian, vehicle-to-vehicle, and vehicle-to-infrastructure communications. In release 15, the V2X feature was further enhanced to support higher data rate, lower latency, and as I said before, to be a bit more reliable. 64QRM was introduced as the new modulation and coding scheme, transmission diversity. Now with release 16, which is still under standardization, the 5G new radio concept is applied to side-link communication. We expect finalization of the standard soon in the first quarter of this year. Now it's important to note that with release 15, our smartphones will be able to use 5G new radio. But at the same time and in the same standard release 15, the direct communication will still be and remain an LTE technology. So now we have a mixture of technology. For vehicle-to-network communication via the UU link, we can use the 5G new radio concept in release 15. When you want to operate direct communication, we have the LTE technology. And as I said, this will be different than from release 16 on, but this standard is still under standardization. Now a few words about the different releases which supports Cellular V2X. Cellular V2X started with release 14, so-called Phase 1, for basic traffic safety services. The standard supports broadcast transmission service without network subscription. It means all road users transmit messages in a fire and forget fashion. This messages carries information in CAN, DENIM or BSM, for instance, position, velocity, steering wheel angle, and so forth. Direct PC5 and mobile network UU communication was introduced, or part of the standard. The operation is clearly in 5.9 GHz frequency spectrum. This is part of the spectrum which can be used in a license-exempt manner. Semi-persistent scheduling is introduced to the system to enhance and increase the spectrum efficiency. The day one use cases are the targeted use cases for this release. Release 15, as I said before, the phase 2 is still an LTE-based system. Transmit diversity is introduced to the standard, the support of 64QRM for higher data rate. The latency is reduced from 20 to almost 10 milliseconds, and carrier aggregation becomes possible to aggregate up to 8 carriers in the PC5 side link. But just to mention it, this carrier aggregation of 8 carriers means at minimum 8 times 10 megahertz to have an aggregated spectrum of 80 megahertz. But this bandwidth is not really available in the world in 5.9 gigahertz. For instance, in China, where we expect the market start in 2020, 2021, 20 megahertz are available. The targeted use case are vehicle platooning, but also the use case I introduced before, see-through for instance, and sensor data sharing. The so-called Phase 3 of cellular V2X will support advanced traffic safety services. It is the release which applies 5G new radio to the site link, which means that the flexible homology we already know from release 15 in the UU link is now part of the site link communication. MIMO transmission becomes possible. Distance-based hybrid automatic repeat request is introduced, an interesting feature, while the Release 14 and Release 15 only support broadcast communication. Release 16 introduces unicast as well as multicast communications. And in this kind of communication, it's possible to use the hybrid automatic repeat request to increase reliability. Let us assume you are driving to an intersection, and now you send a message for an intersection movement assist. This message is only relevant to cars in a close proximity. A car knows that it is in close proximity from positioning information which is transmitted in the cycling control information. For this purpose, the cycling control information has a two-stage protocol. And from the second stage, cars can estimate and can learn if they belong to the area of relevance, and they can join this multicast group and can answer to the transmission, whether it's correctly received or not, which will tremendously increase the reliability of the system. V2X target then not only the frequency range number 1, which are the frequencies in the lower gigahertz spectrum, but also that of the millimeter wave spectrum in frequency range number 2. The targeted use case here are, for instance, high-density platooning, remote driving, and advanced sensor data sharing. A few words about the spectrum situation in the world. In the US, in 5.9 gigahertz, we have 7 times 10 megahertz available for ITS communications, but here, according to the rule of the Federal Communications Commission, only IEEE 802.11p DSSC technology is permitted to operate in the spectrum. Recently, the FCC announced a notice of proposed rulemaking to change the situation and to reform the spectrum to give at least 20 megahertz to cellular V2X and to keep 10 megahertz for DSSC. There's now an ongoing comment period, and we expect the finalization of the process by end of this year. The situation in Europe is quite complex. In Europe, the spectrum in 5.9 gigahertz is in general technology neutral. It means you can operate either cellular V2X or IEEE 802.11p, but you need to at least support ITS services. Volkswagen recently rolled out the ID.3 and Golf number 8, which are equipped per default with IEEE 802.11p technology. Now it's a question, what will happen if another car manufacturer brings cellular V2X to the market? Then we have a coexistence issue in the 5.9 gigahertz spectrum. In China, it's clear we have here 20 megahertz available in 5.9 gigahertz, but only cellular V2X is permitted to use the spectrum. And as I often said in this presentation, market rollout of the technology is expected second half of 2020, beginning in the first half of 2021. The vision and the aim of intelligent transportation system is to increase road traffic safety by exchanging messages between road users. Some of the use cases I introduced before, they require a certain market penetration to bring benefit. It makes no sense that only cars belonging to the same brand are able to communicate with each other. Interoperability is key. But how can we establish and achieve interoperability in cellular V2X? To explain it, let's have a look to the mobile communications industry, and let's look how the mobile communication industry achieved this interoperability, which has led to the global market we have today for our smartphones. They do it, or they achieve it, by testing on different levels, starting with compliance testing, which is mainly regulatory testing, to check if the output power is below the limit, shock resistance, or in Europe the Radio Equipment Directive. You will get, for instance, the CE sign for it. In addition to that, the mobile communication industry decided to establish a conformance test framework. It's an industry-recognized scheme which is voluntarily applied. The mobile network operators require this kind of conformance testing of all of our smartphones to make sure that no smartphone, no device will harm any network in the world. In addition to that, all manufacturers, of course, are free to apply their own in-house test specifications for quality testing and performance testing. Now the industry wants to encourage the automotive industry to first think about a similar conformance test framework or to reuse the already existing one. We have here players like the Global Certification Forum, for instance. The GCF is responsible for doing the certification of our devices. We, ROHDE SCHWARZ, we support our customers, we support you to develop cellular V2X devices. We have the world's first and only protocol conformance test solution in the market. We have a test system to test the application in terms of end-to-end ITS scenario-based testing in laboratory environment. In the last year, in 2019, we supported our partners and the industry with testing in different plug fests and plug tests around the globe. In China, in Europe, with a focus on the US stack, on the European Union stack, and on the stack which is operated in China. In addition to that, we have also solutions for full vehicle testing, for chamber testing, for electromagnetic compatibility testing, over-the-air testing, and radar testing. CMW100 is our production test solution to verify the RF performance. CMW500, our mobile communication tester, in conjunction with the SMBV for GNSS emulation, is used for certification of C-V2X according to the GCF work items 281 and 282. In addition to that, we offer an application test solution together with our partner Vector. This application test solution has the focus on end-to-end ITS scenario-based testing. Our product portfolio covered the whole stack, starting from the physical layer, RF performance, to that of the application layers for end-to-end ITS scenarios testing. Thank you very much for listening.